So ordinary least squares modeling. The default generic model, you need to do nonlinear regression, then you need to do numerical optimization. It could be, say, Newton-Raphson steps, it could be other more fancy methods. At the end of the day, you need to do some numerical optimization. Now, if you have a general linear model, then you can write up a closed form solution to that. So we can write all the observations here in one vector. Then we have all the predictors here, where each row here corresponds to one time point, multiplied on our parameters, and then plus a vector of our epsilons. So what we want to do is, and then we'll define this x here, which is a combination of all the predictors here in one vector. We call it the design matrix, because that's kind of how the design of the experiment, if you were to pick it yourself. Sometimes you're observing it and you cannot change it, but in general, sometimes you can do it. Now, what you want to minimize is the sum of squared errors, just as we looked at before. Now, how do we do that? First of all, we have to look at what are the prediction errors. So, first of all, what we do is we look at this up here, the epsilon at time t. What is that? Well, we look at the s of theta, epsilon at time t. We get that by looking at the prediction error. So that's our vector of observations minus our predictions that we got from x times theta. We need to transpose that, and then we multiply with itself. So in order to find the optimal values, to minimize this, what we should do is we should differentiate this expression with respect to theta and set that equals to 0. So if we do that, we want to solve differentiate of s of theta, and we want to solve that equal to 0, but let's just look at what it gives here. Now, this is a quadratic term, and some, you can say, more complicated linear algebra leads us to that this is equal to minus 2 times x transpose on y minus x theta. If you look at it in a typical univariate setting, well, basically, if you have a quadratic part, you want to differentiate that, then you have, you can say, the inner part differentiate 2 times to get the quadratic part, and then you have the inner part differentiated, that gives you the x, and then you have it yourself there left. So it does make sense, this also from intuition. Now, with this, we want to equate that equal to 0, and then we want to solve this. So the minus 2 factor here really doesn't matter, since we're just solving equal to 0. So what we have is that we have x transpose y. I'll take it to the other side. X transpose x on theta on one side, and then on the other side we have x transpose y. This is what is called the normal equation, and from a numerical point of view, this is what you want to solve. You want to find this matrix A, and you want to find this vector here, and then you solve for the unknown elements theta here. What we do in analytical setting is that if x transpose x is invertible, then we will calculate our theta, and we indicate that it's an estimate by adding a hat here is equal to, we pre-multiply x transpose x on, so the inverse of that, we pre-multiply that on x transpose y, and that is our estimator. So that's what we have over here. Now, there we need to estimate our variance. We posted this before, and then we just look at what is the variance of this here. Now, what did we do earlier on? We have various ways to look at this. I can just postulate it here, but I can also show you how it works out. So, how to do that? There are basically two ways. We can go this way and say we just need to differentiate once more. That's the easy way. So because we already differentiated once, and if we were to differentiate this again with respect to theta, what do we get? Let's do that down here. So we differentiate with respect to theta what we already differentiated here. Let me write it like this way, just to clarify what we're doing. And what we then have is that we have a minus here, but we also have a minus in there. So then the y does not contribute. So what do we get? We get still the 2 here. And then we have x transpose on x theta. So that gives us x transpose x. And now if we take this, first of all, we notice that this is a positive number, always, which means a number, it's curvature as well. So basically this means that if you have a positive curvature, it means you have found a minimum when we found here. That was also what we assumed, but now we checked it. And if we plug this in up here, what do we get? We get that the variance of theta is equal to 2 times sigma hat square, but you're going to multiply by the inverse of what we found down here, so the 2 cancels out. So we have sigma hat square times the inverse of x transpose x here. So that's the simple way to prove what the variance is of the ordinary least squares estimator. A very quick example. We have 5 observations in this case. We have a predictor set, and we have observations y. And we'll assume the model that we postulated in the beginning, and here are the data. The red dots are the observations, and the greenish dots are the predictors. So how do we do this? Well, we want to write it on this form so we can do the matrix matrix observations. In order to have this represent this model, we need theta 0 here. In order to represent that, we need a column of 1s here to be multiplied by our estimate of theta 0. Then we have a column of all the set values copied from over there. And then we need a column with set square. And then we have everything set up. We will have a vector of observations. And we just need to do the calculation of x transpose x inverse, pre-multiply that on x transpose y. And then we get some estimates down here. That's all there is to that. And of course you can also calculate the variance of this, but we'll skip that for now. And when we've done this, we want to look at how did this perform. So we have the red line here are the observations as a function of time here, and then we have the predicted values as well as green. And if you look at the bottom display here, then we look at the residuals as the difference between the two. And we notice that the scale here is much smaller than the scale up there. So generally we're happy. Of course, we should not make too much inference from a model with only 5 observations, but that's a totally different story. Now, if we look at this general linear model and use the ordinary least squares estimator, how is that actually behaving? What are the properties of this estimator? First of all, it's a linear function of the observations. And how do we see that? Well, if we look at the estimator that we have here, what we have is that we have all the observations out here, and we have a matrix x transpose x inverse x transpose. We just pre-multiply that, so we can look at this as an operator that we pre-multiply on y. This L here, we call that the hat matrix. So that's one thing. It's an unbiased estimator, so the expectation of our estimator is the true value. And we have this variance we discussed before, and it is what is called blue. It's the best linear, unbiased estimator. So it has the smallest variance among all the estimators that are linear function of the observations. You can make other estimators, but then they have other properties as well.